equations. Now, this paper is worth 2 days worth of work. So, because we're not going to get to all of the types of balancing reactions today. There are different, not rules. I'm going to show you some tricks. So we're focusing on the easier ones today, the addition, the decomposition, the single and double replacement, but not combustion. And we're also focusing today on the types of reactions where if there's polyatomics, they're on both sides of that arrow. Because sometimes they're only on one side and not the other, and that can make it a little bit more difficult. So those two things are tomorrow. So this assignment, if you've already picked it up, the ones that you should be able to do after I explain how to balance today are number 1, number 2, number 4, number 5, number 9, and number 10. Because they're going to follow the rules that we're going to talk about today. Whereas the combustions, 6, 7, and 8, and then number 3 on the front, that's more of what tomorrow's lesson is. Keep in mind, I'm technically on campus tomorrow, but I'm going to be in the library with this meeting with Region 11. I don't see anybody else online. And so that means I've already pre-recorded it. I've already uploaded what I was doing into Canvas. I did come across one where I had put the wrong number, the wrong subscript down on the bottom. So there's like a 1.5-minute pause where I'm fixing it real quick, where I blank out my screen so you cannot see what I'm doing. And then I come back and I also explain what I did wrong. I have no idea who your sub is, but I will be back Friday. And Friday I was planning on having a balancing workday anyways, in case you were having problems. So if tomorrow's with combustions, which are the hardest type to balance, if you had problems, then I should be able to fix it Friday. That's what we're doing the rest of this week. For the opener, since we are talking about balancing these things now, what does it mean if something is balanced? But what does it mean? Like, don't just tell me it's balanced. What does it mean if something is balanced? Okay, I heard way is the same. What was over here? What did you say for balance? You didn't? I thought I heard another one. Right, and pull your thing up. Y'all stop eating in here and pull these up. What else could it mean if something was balanced? Yes, weighs the same. You said what? When we do charges, yes. Yeah, that's more what I'm looking for. Both sides are going to be what? You can't use the word that you're trying to. There we go. Both sides are equal. That was what I was looking for. Now, what does it mean if something is conserved? No. If it's conserved, what does that mean? What now? No. There's the law of conservation of energy, and there's the law of conservation of mass, and there's the law of conservation of matter. What does that mean between a starting and an ending amount if it's conserved? Okay, good. Okay, so what conservation means is things might be rearranged, but the net beginning and the net ending value are the same. It's the same concept as being balanced. But balance just means like if you put it on a seesaw, like you don't have this. Or it's straight. It's equally weighted, which is what Luke said. What conserved means is, yeah, you got your compounds over here in the reactants, and then you've got your compounds over here in the products, and they might be in a different arrangement, but you still have the same amount on both sides. That is what we are doing today. I think this is first. This is first. So conserved means that you rearranged the things that you started with, but as a whole, you didn't lose anything. They're in a different arrangement. Now, some of the words that are on here, we actually talked about yesterday, and if you did not submit that very easy assignment, that Google Slides assignment from yesterday, you need to do so. I did not check that yet. If we have time when I get through this, I will go through and let you know who did not turn that in, because that should have been a very, very easy grade for you. No, there was a Google slide that went with it. What was the question over here?
It's not finished at all.
Well, I mean, it's still open. I'll let you know if I haven't received it. The law of conservation of mass, okay, says that the matter, the atoms, the mass itself, the elements themselves, says that they're going to however many you start with, which are your reactants, or reactant if it's a decomposition. The subscripts that you have, they need to equal the total of the subscripts on the product side. Sometimes the skeletons are already balanced. It's a 1-to-1 ratio on both sides. It's perfect, but that's rare. Normally, the numbers that are representing the atoms on the reactant side are not the same as the numbers that are representing the elements on the product side. And we have to use those coefficients, those numbers that we had in the front, we multiply everything to fix it. I just need to teach you how to do the math today. And I am going to show you the long way, the way that we're supposed to do it. And then I'm going to show you the way that I do it in my head. Well, not that I can show you what's going on inside my head, but I can talk through the way that my brain processes these skeleton equations. A skeleton equation, like I said, sometimes you're lucky. Normally it's not balanced, which means that your values, your total numbers on your reactants are different than your total numbers of your products. But when you fix it and you put those coefficients in the front, it makes the number of reactants the same as the number of products. We call that a balanced chemical equation. Those coefficients. So if I put, and I know they can't see it online, but if I do this, this number, what we were doing yesterday, that has to multiply everything that's behind it in that compound. It only affects this compound. If it was like plus water or something over here, that 3 wouldn't affect the other compounds. Just need to teach you how to do it. And I'm hoping I don't have any weird typos like I caught the one on tomorrow's, but I did fix that. Like I said, there's just a short pause. You can hear me rationalizing it as I'm fixing it because, like I said, combustions, they can be nasty. And combustions are the only ones that I actually have to work out longhand still. It's rare. Now, the coefficients in combustions can be in the 50s. Normally, they're not. Now, the subscript is this little number. So on the board, for those of you who are remote that can't see, I have a coefficient 3. Then I have Mg for magnesium and open parentheses, the capital OH close parentheses for the hydroxide, and I have a little 2 outside. That little 2 that's outside of the parentheses that's on the board, that's a subscript. You guys were doing this yesterday when we were counting the atoms. The subscript only affects its individual element, or if it's outside of parentheses, it only affects the thing that's inside parentheses. And that was in yesterday's opener and yesterday's assignment. The coefficient, once again, is the number in the front. That is a multiplier. The subscript is outside of parentheses. That is also a multiplier. It's just next to an element like this. Let's see, like this. That 2 only affects the chlorine. So what I wrote on the board, for those of you that are remote, wrote calcium chloride, and the formula is CaCl2. That 2 only affects the chlorine. So this compound has 1 calcium for every 2 chlorines. Compound above it, there's 1 magnesium for every 2 hydroxides. I just put a 3 coefficient in the front. So coefficients multiply everything in the compound, just that compound. Subscripts only affect the element that it's next to, unless it's outside of parentheses, and then affects everything that's inside parentheses. No, coefficients will always be in the front. And I know when I normally do, my personal worksheets, what I normally do is this. So we think of one, right? So I personally, when I do these, I put blanks to let you know that that's where the coefficient is. I'm sort of using the ones that this district likes to do, and they didn't put that line in the front. But if it helps you, you can put the blanks in the front to let you know that that's where the coefficient has to go. And we'll work through one of these together, probably, if we have time. I don't want to go too fast. Are y'all through with this one? All I know is cold. My toes are cold. They hurt. Well, when the heater finally does kick on, you guys are all going to get hit with an Arctic blast until it starts heating up, and then it's like a sauna for a short period of time. But like I said, skeletons, this is a skeleton equation. What I have on the board is iron reacts with oxygen gas to create iron trioxide. And when you write the symbols down, it's Fe plus O2 makes Fe2O3. It's not balanced. A non-balanced equation is a skeleton equation. If it's not balanced, we have to figure out which numbers go where so that both sides have the same value. Some of them are very simple. Some of them take a little bit of extra thought. I highly, highly, highly recommend using pencil at this point and having an eraser. You will put down a number that originally fixes it, and then you're going to put in a different coefficient that's going to make your original number wrong. There's nothing wrong with adjusting your coefficients. And if you end up having like 2, 2, 4, it really should be 1, 1, 2. So coefficients multiply. You have to have the same amount on both sides. We're going to treat this arrow as an equal sign. Whoops, I apologize. The arrow is an equal sign to sort of turn it into a math problem, because we're about to do a whole bunch of math in this class for the rest of the year. Sorry. Right now we're just multiplying and sometimes adding, which is the case of a combustion, which is what makes combustions harder. And like I said, I'm going to give you some tips or tricks that I've picked up in all the years that I've taught chemistry, things to look out for to try to keep you from having to go back and change the numbers that you originally put there. Rule of thumb. Well, first of all, we read left to right, top to bottom. Okay, so when we're identifying, doing the math underneath it, the way that the one I have on the board, I would list iron first, and then oxygen second, because we read left to right, top to bottom. And then I would make sure that it's the same order on both sides. I don't care the way that they're written out on the product side, because you're going to be balancing them linearly. If you start putting them in different spots, you're going to get confused. We will start with elements that are only listed once on each side, which is what makes combustions harder. If a polyatomic is on both sides, trust me, please, and leave them together. So if I had phosphate on both sides, PO4, you would write it as PO4. Only split a polyatomic ion if it's only on one side and not the other. And that's actually the harder part that's tomorrow, which I think is number 3 on the front. That's why I would skip number 3 if you're trying. Like I said, this paper is for 2 days. If you have an odd amount on one side, like this iron has 1, and an even amount on the other side, on the right-hand side, it's got 2, you cannot make an even number odd, okay? But you can make an odd number even. You would be multiplying it by some type of even coefficient. 95 times out of 100, doubling it works. If doubling isn't enough, it might be times 4 or times 6. But your odd number, wherever that is the problem child. And we somehow have to get it to be an even source if the other side of the equation is also even. That's it. Combustions. I tried to be as descriptive as possible with the thing that I recorded for you guys for tomorrow. I am expecting questions on Friday. I'll be on campus and just stuck in the library all day. No, I'll be here Friday. We have a meeting in the library with Region 11, the chemistry teachers do. I have no idea what it's about, but we have a meeting. If you have an element that's listed twice, either on the reactant side, okay, or twice on the product side, leave it for last, okay, and do not add them together already. So like in the case of a combustion, if I write the generic formula on the board, which is I have so many carbons, so many hydrogens, sometimes oxygens, but I'm going to have oxygen gas, and it's going to make carbon dioxide and water. What makes combustions hard is the fact that I have two different sources of oxygen. I have two in the carbon dioxide and one more in the water, which I know 2 + 1 is 3, but you can't balance them together because a number here only affects this oxygen. That's it. A number here only affects this oxygen. So you leave oxygen gas for last in a combustion, but that is actually tomorrow's lesson specifically. There is no problem having to change a coefficient because you didn't put a large enough number there. But if you change a coefficient, you need to redo all your math and you need to double check everything starting from the top. Every time you change a number, you need to start over again at the top and make sure you didn't mess something up. Once we start working these, you will see what I'm talking about. I did not print out my notes for this. I forgot to. Let's see, where are we at? Okay, so we're ready to start with the examples. Y'all ready to do the creation of water? This is how I have taught how to balance for forever. You know, this is not how I do it in my head. Right? No, it's not. So you have the skeleton. You have hydrogen gas reacts with oxygen gas to produce water. What I've always taught my students to do is to draw a line straight underneath the arrow, and this is going to help keep it separate, the reactants on the left and the products on the right. And then I highly recommend that you write them in the order that we read them. So I know they can't see me pointing. I see hydrogen first, so I'm going to list it first. I see oxygen second, I'm going to list it second. Now you need to make sure, and this is one of those, please just trust me, because you're going to get confused if you don't do it this way. They happen to be in the same order on the product side, but if they're not, list them in the same order that you wrote them on the reactant side. Please do it that way so you do not get confused. Now I need to figure out how many I have of each. According to the reactant side, how many hydrogens are on the reactant side? 2. Okay, now we're going to do oxygen. How many oxygens are on the reactant side? 2. So far, so good. All right, on the right-hand side, how many hydrogens do you have? 2. And how many oxygens do you have? 1. Okay, so the hydrogen is not the problem child. Oxygen seems to always be the problem child when we're balancing. Now, you cannot add, okay, you cannot divide, you cannot subtract. The only thing I can do is multiply. And how am I going to make the oxygens the same smallest value? What am I going to multiply this one by to make it equal to the reactant side? I want these to be the same number. What can I do to this side to make them both equal? Like multiply by what? By 2. The oxygen. This is not the problem, y'all. This is the problem. So it's not the number you're turning it into that goes in front of the compound. It's your multiplier. It just so happens to be the same number on this problem. So guess where this 2 has to go to change the product oxygen to have 2? Where does this guy have to go? The red 2. No, not in front of in front of, right here. In front of the compound that contains that odd number of oxygen. This is what people do wrong. You have to distribute That is why we did yesterday's stuff when we did it. I don't have 2 hydrogens anymore. How many do I have now on the right-hand side? I have 4 of them. Most of my students, when we first start balancing, they forget to distribute or to multiply out if you don't like the word distribute. Well, I changed the number, so I have to start over at the top. Is 2 equal to 4? No, so what am I going to do to this side to make them even? Times it by 2. Where does this 2 go? In front of the hydrogen. Does that change anything else? No, there's nothing else there. It's just hydrogen gas. So now we're going to double check it again. Is 4 equal to 4? Is 2 equal to 2? So guess what the missing number is everything's okay. What can I put there and not change anything else? A 1. Some teachers don't put 1s in front of compounds. I was taught to put a 1 as your coefficient in the blank. Just like I was taught to either do +1 or -1, and some teachers either just plus or minus by itself means 1. Go ahead and put, when you're done and everything's balanced, if there's an open hole, like there was in front of the oxygen, put a 1 in its place. Now, when we start doing stoichiometry, which is a while, I think it's next 6 weeks, these numbers, these are extremely important to change from one substance into another. So like I said, guys, you've got to be able to create your formula right, because if you don't have the right subscripts, the balancing isn't right. And if the balancing, if these numbers, these mole coefficients aren't right, then the rest of the math isn't right. So everything is crucial, being able to know that these are diatomic elements and that they have 2. And you should know by now that water is H2O. You know, before I move on to this is one of the easiest ones you can do. Are there any questions on this one? If I asked for the coefficients, like if that's what I was asking as a multiple choice answer, it would be 2, 1, 2. This is a correctly balanced equation. And this is an addition reaction, just in case. Okay, but I don't necessarily, on the blank, you can write addition if you want to, but the order of the coefficients is supposed to go there. So it would be 2, 1, 2, and you really should put commas in between them, because otherwise it might be 212. And like I said, we do sometimes have coefficients in the 20s and the 40s. It's not common. All right. One that's I meant to, hey, it was a double replacement reaction. I forgot to, what happens when I don't proofread? Okay, so once again, we read left to right, top to bottom. So I'm going to do cobalt first, bromine next, sodium third, and the phosphorus last. And I do not care the order that they are written up in the equation. Keep them in the same order. So then I'm going to rewrite cobalt, bromine, sodium, phosphorus. And yes, I do personally draw that line straight underneath the arrow, so I make sure that my math for my reactants is obviously separate from my marks. I'll give you a second to look right now. Make sure we all know how many we have of each. I'm hoping I get through all of these. How many are there? Oh, huge. All right, so on the left, how many cobalts are there? 1. No subscript means 1. How many bromine atoms are there? 3. How many sodium atoms are there? 3. And how many phosphorus if there's no subscript? 1. Okay, so now on the right, cobalts first. How many cobalts do you have? 1. Go to bromine next. How many bromines do you have? 1. How many sodiums? 1. And how many phosphorus atoms? 1. Right? Any questions how I figured out how many? Once again, that's what we did yesterday. Was identifying how many atoms. All right, let's start at the top. Is 1 equal to 1? Is 3 equal to 1? No. What am I going to multiply the one on the right by to make it equal to the side on the left? A 3. And where does this 3 multiplier go? Where do I have to put it to change the bromine? Right here, in front of this compound. Distribute. What else does the 3 change? It doesn't just leapfrog over here. What does it do to the sodium? It also is going to do times 3. It doesn't change anything else. Now I get to start back over. Is 1 equal to 1?
Yes.
Is 3 equal to 3?
Yes.
Is 3 equal to 3?
Yes.
And is 1 equal to 1? So that means that those 3 missing numbers should all be the number 1. I only had to change the 1. It just looked harder than the one before because there was more stuff. Some of the hardest looking ones are actually the easiest ones to balance. So yes, it's a double replacement, but that blank on the side wanted to know the coefficient order, so it would be 1, 1, 1, 3. But yes, this is an example of a double replacement reaction. Are there questions how I got the numbers? The red 3 or no? Some of you guys, you will pick up on this like crazy. Some of you will do the math like this underneath. Some of you will go, okay, I have 1 and 1, I have 3 and 1. Well, I got to put a 3 here. I've got 3 and now I have 3 and I have 1 and I have 1. I literally will do that with my fingers side by side. Some of you are going to prefer to do this. Okay. Potassium is first. How many, and it's in the same order, potassium, iodine, fluorine. Like I said, you're going to want to be ordering them and multiplying them side by side. So just keep them in the same order. How many potassiums are on the left? 1. How many iodines?
1.
How many fluorines?
2.
2. Fluorine is one of those 7 elements. On the right, in the same order, how many potassiums?
1.
How many iodines?
2.
And how many fluorines?
1.
Okay. Is 1 equal to 1 on the top?
Yes.
Is 1 equal to 2 in the middle?
No.
So I'm going to do times 2. I should have put, I guess I changed that one first. It doesn't really matter. Normally I do top to bottom. I need to put, so normally I would have, yeah, I totally need to change. I started with fluorine is what I did. Here, let me go backwards and I'll start with fluorine. Doesn't matter if you start with one or the other, it'll look the same thing. All right, so I actually started down here. You could have did times 2, put the 2 here, distributed it to the potassium, multiplied it by over here by 2, which would have changed the fluorine. I did it reverse for some reason. I did, starting with the fluorine, I put the 2 in front of the potassium fluoride ion, and then I distributed it. Same exact thing would have happened if I would have done it the other way. Then I said, okay, now I'm going to fix my potassium. And in the process of fixing the potassium, I fixed the iodine. Why did I multiply what? Why did I get this here? Because when I first started, because I started down here, and I did times 2 to make the fluorines equal, but then I distributed it to the potassium. That is what people forget to do. This 2 doesn't just multiply the fluorine, it multiplies that 2, and so then I had to start back over. 2 and 1 were not equal, times 2, which fixed the iodine. This particular one is a single replacement reaction. My 2 missing numbers were 1. So the coefficient order would be 2, 1, 2, 1. Like I said, these are the easier ones. They get a little harder. Which one do we live in? Ah, the one that's on the board. This one. The creation of rust. We only have iron and oxygen. They actually are in the same order on both sides, from left to right. On the left, how many irons do you have?
1.
Just 1. How many oxygens do you have on the left?
2.
Okay, on the right, how many irons do you have?
2.
How many oxygens do you have?
3.
Now, I know not to start with iron. I know not to, because I've balanced this thing for forever. I'm going to explain to you why I know that I'm not going to start with the iron. You would normally want to multiply by 2, right? Okay, that doesn't affect anything. But then when I come down to the oxygen, the left side has 2, the right side has 3. When you have an odd on one side and not the other, you almost always start by doubling the odd. Oxygen is always your biggest freaking pain in the butt. It causes problems left and right. The least, or the first number that these two both divide into evenly is 6. So I would do the right side by 2, and I would do the left side by 6, or by 3. Okay, so this 2 is going to go up in front of the rust. Do not forget to distribute it to the iron. Now I needed to fix, I should have done the oxygen next. Yes, I did. That 3 doesn't affect anybody. Okay, now, how do you fix the iron? Because that 2 will not fix this. You need to multiply it by 4. So and this is a addition or combination or synthesis, and it would be 4, 3, 2. Like I said, I have done so many balancing equations. I know that oxygen, depending on the type of equation, either you leave it for last or you double check it first. And this is the type of one where you're going to double check it first. Now, if you would have done 2 here and then come down, then you would have realized that I needed to double that 2, which is why I said I would use pencil. You may start balancing it correctly, but as you start changing these numbers, realize I didn't put a big enough coefficient in front of that compound. There is nothing wrong with changing them as long as you are going up. And then always double check. Like if you would have done 8, 6, 4, you needed to divide everything by 2 because you balanced it too much. Once again, it just looks hard. You see sodium first. You see, now, see how phosphate is on both sides? This is another one of those, please just trust me. Keep them together if they're on both sides. Please, please do not separate them unless you have to. You will not understand what you're doing if you do 1 phosphorus and 4 oxide. Like, please leave polyatomics together. You won't figure it out. I have silver on both sides. Nitrate is on both sides, so I'm going to keep nitrate together. You only break apart a polyatomic if it's like number 3 on the homework paper, if you guys have it. The carbonate is on one side and it's not on the other. So I can't leave the carbonate together with number 3. I have to break it apart. You don't do that here. How many sodiums are on the left? 3. How many phosphates are on the left if there are no parentheses? No. 1. Y'all, that 4 is attached. It's part of the phosphate ion. How many silvers are on the left?
1.
There's no parentheses, so how many nitrates are on the left?
1.
1. Just make sure you're doing it in the same order, because we don't.
Why is it 3?
These, because that ion, the phosphate ion, is 1 phosphorus that is bonded to 4 oxygens, and that whole ion carries a -3 charge. It's like they're super glued together. If you tried to break them apart, you'd have 1 sodium, 1 phosphorus, 4 oxygens plus 3 more oxygens. Silver would be 1 and nitrogen would be 1. Don't, please don't. On the right-hand side, you have 1 sodium. You've got how many phosphates? 1. How many silvers? 3. And how many nitrates? 1. Now you can start fixing it. Starting at the top, 3 is not equal to 1. What am I going to multiply this side to make them the same number? By 3. That's going to go in front of the compound that contains that sodium ion. Now I have to distribute it to nitrate. Now I don't have 1 nitrate. How many do I have? 3. Didn't change anything else. I can start back over at the top. I now successfully have 3 equals 3. 1 equals 1. Uh-oh. How do you fix this one? 3 and 1 are not equal to each other. Over here times 3. This 3 goes up in front of the silver compound. Well, look what it just did to this nitrate. It multiplied it by 3. Okay, even though I know I'm done. 3 is equal to 3, 1 is equal to 1, 3 is equal to 3, and 3 is equal to 3. That means that those 2 missing holes will be 1s. And this is a double replacement reaction. One more we're going to do. How many of you are actually understanding? You're seeing the order that this is doing. Some of you are like, oh, this is easy until we get to combustions. And some of you are like, I don't know what you're talking about.
Pretty easy.
Oh, I understand. But like I said, combustions are a little bit more difficult.
I know how it works. I know.
Now, if I show you the way that I do it, because this literally, like, this is how my brain processes this. I have 1 and I have 3. What would I normally put here? By 3, which means I have 3 times 4 is how many chlorates? 3 times 4 is 12. I only have 1 over here. So if this is worth 12, what would I put here to make this guy times 12? What? No. No. That is 1 chlorate. And when I put the 3 here, I have 3 times 4, which is 12. I have 1 of them here. What would I put here to make it to 12? You're not ready for me to show you how I do them. All right. 10 is 1. Chlorate is 4. Potassium is 3. No parentheses. How many phosphates do I have? 1. On the right. How many tins? 3. How many chlorates? 1. How many potassiums? 1. How many phosphates? 4. It's the number outside the parentheses. You're not ready for me to show you the way I do it. What did we say? How do we make these equal? You got this part right when I was pointing at them. How do you make 1 and 3 equal to each other? We're going to do multiply. Times 3 goes up here in front of the 10. You distribute to the chlorate. 3 times 4 is 12. I've got to double check. All right, 3 is equal to 3. How do I fix the second line? Times 12. I want them equal to each other. This 12 goes in front of that, but now I need to distribute to the potassium. So I don't have 1 potassium anymore. I have, no. 1 times 12 is 12. Start over again. 3 is equal to 3. 12 is equal to 12. How do I make 3 and 12 the same number? What do I do to the left side? Times 4. This goes in front. This goes in front of the compounds. Hold on. Distribute it to the phosphates. 1 times 4 is how many? 4. Okay, start over again. 3 is equal to 3. 12 is equal to 12. 12 is equal to 12, and 4 is equal to 4. So what's that missing number in front of the 10? 1. This is also a double replacement reaction. The mole or the coefficient order would be 3, 4, 12, 1. 3, 4, 12, 1. This is the most complex one that I've shown you how to do. Like I said, the numbers in the front, they are not always single digits. I have one more thing on here. I know we are. Y'all, if it's even on one side and odd on the other, 9 times out of 10, double the odd. Okay? It might have to be times 4 or times 6 or times 8 or times 10. But that is what you should start with. Now, what you should be able to do is number 1, 2, 4. Well, let me tell you, you should be able to do 1, 2, 4. 5, 9, and 10. I'm not expecting you to be able to do the combustions yet. I'm not. You should be able to do 1, 2, 4, 5, 9, and 10. I would not try to do the other ones right now.
Those are all the ones you do right now?
Those are the ones. Now keep in mind, I'm not here tomorrow. Like I'm here, but I'm not here. And yeah, I expect questions on the combustion stuff that I'm leaving for you to do tomorrow. Everything will be in Canvas. I did not take attendance in here, I don't think. Matthew's not here. Sebastian's not here. We don't know if Sebastian's quarantined. Are there any like, could you go back over that again right now? I do try to make this part as easy as possible. This is one of those crucial steps for the rest of the year.
Right.
What?